是大光头。
Okay, let's get started. So today we'll just talk about categorizing types of rings pretty much. So let me just remind you all, we don't like zero divisors. Yeah, it's the fact that, but both are not, it's possible both are not zero, right? Because like the usual rings we know, right, R, Q, they have no zero divisors, right? It's because when you multiply two things, if you get zero, one of it has to be zero, right? So an important thing to note is they do have one. They do have one, like the multiplicative identity, right? Let's. Okay, so knowing that, so note there are rings without zero divisors, right? And without one, right? Can anyone tell me one? What ring is there that like has no zero divisors, but also does not have one in it? Yeah, so example would be like 2z, right? The set of even numbers under addition and multiplication, right? In general, nz for n bigger than 1 won't have 1, right? A question, what about the set of odd numbers? Is that a ring under addition and multiplication? Yeah, it's far from it, right? Like even addition, if you take the set of odd numbers under addition and multiplication, it's not even closed under addition, right? Addition is not even a binary operation because odd plus odd is not odd. So, okay, so a ring with multiplicative identity is called a ring with unity. Yeah, so unity is like 1 pretty much, right? So, we call like the identity element to be the unity. Okay, So with one, we could define like inverses now, right? So note in the axioms for a ring, we don't require inverses for the multiplication part, right? So we say let R be a ring with unity. Go back. So of course we want to later on when I write one is not zero, ring with unity, right? So a ring with one not equal to zero. So really the only time this is the case is when, you know, you have the zero ring. So it's just the set zero, the set of one element. So you can see in that case, one is zero, right? But other than that, one, the multiplicative identity is different from the additive identity. So we say an element U in R is a unit. So do not confuse unit with unity. Yeah, by unity we mean one, but unit is you know, unit and unity are two different things. Of R, right? So a unit is just means if it has multiplicative inverse. Has multiplicative inverse in R. So if every non-zero element of R is a unit, then we say R is a division ring. Right? So in other words, if every element, non-zero element, because zero is not invertible, obviously. If every non-zero element is basically invertible with respect to multiplication, then it's called division ring. And the best part is a field is a commutative division ring. So again, in the axioms of a ring, we don't require A times B is B times A, right? So we want to include stuff like matrices. Okay. So let's do examples, right? Just so we all have, you know, clear examples in our head. So let me just ask ring, division ring, field, and let's say units. Yeah. Okay, let's do the first one. Let's start off easy. The integers under addition and multiplication, is it a ring? Yes or no? Yes. Okay, what about division ring? So is every non-zero element invertible?
No. Oh, yes.
No. Invertible inside the set. Yeah. So 2 is not invertible, right? Because 1/2 does not belong to integer, right? Does not belong to z. So obviously a field is a commutative division ring, right? So if it's not a division ring, it can't really be a field, right? So field, no. So what are the units in this case? So what elements do have inverses? Multiplicative inverses. 1 and -1, right? Because inverse of -1 is -1. Okay. Q, let's do rationals under addition and multiplication. So is this a ring? How about let's start there. So yes. So okay, is it a division ring? So is every non-zero element invertible inside the set? Invertible and the inverse, belongs inside the set. Yeah, right. So I mean, the inverse of m over n is n over n, or the inverse of like r over s is s over r, right? So this is true. So is it a field? So is multiplication commutative here? So it is a division ring. We check that. So a field is a commutative division ring. So does multiplication commute for rational numbers? Okay. And what are the units in this case? So a field, right? A field, everything's a unit, right? Except zero. So it's just the whole set without zero, right? Okay. Now let's take z mod 20z under addition and multiplication. So is this a ring? So hopefully you could check this, right? So what about division ring? Is every non-zero element invertible? Yeah, z mod 20z. Yeah, sorry. 20. This is... just rewrite it. Yeah, this is z mod 20z. So is every element invertible here? Every non-zero element, sorry. Yeah, it's the stuff that share a factor with 20 is anything with GCD bigger than 1 doesn't, right? So obvious it's not a division ring, so it's not a field. Okay, so I think I gave the answer away. So if, everything that's GCD bigger than 1 is not invertible, which ones are invertible? Yeah, so A where GCD of A and 20 is 1, right? Stuff that are co-prime with 20, right? So does everyone remember why this is true? So do you all remember the fact that if GCD of two numbers, if GCD of mn equals d, then there exists AB such that MA plus NB is D? Do you all remember that? Or remember this? Ring a bell? Euclidean division? Okay, well, this is a fact. So here, right, using this fact, right, if there exists AB such that maybe I used the wrong letters. So let's use CD or EF. So here, right, GCD is 1, so there exists EF such that AE plus 20F is 1, right? So from here, what happens if I mod 20 the whole equation? what happens with the 20f when I mod 20? What is 20 times f? I don't care what f is. What is 20 times f when I mod 20? Right, because I want to be in 0, right? So AE equals 1 mod 20, right? If you like congruent. So E equals A inverse. Yeah. So A is invertible. So this precisely says A is unit, right? Because the inverse is E. So yeah. Okay, so that's just a reminder, right? So this is just review. I mean, this is from like group theory. Group theory and like Euclidean algorithm. So yeah, so that's the answer for that. So what about stuff like this? 7z. Knowing this, right, obviously it's a ring. And going back, right, we say all the invertible elements is stuff coprime, right? But what numbers are coprime to a prime number? If I gave you a prime number, basically everything other than then like 0 is coprime to it, right? Everything from 1 to 6 is coprime, right? Because definition of prime is you don't share any factor other than itself and 1, right? So you see here, this is true, right? And obviously multiplication commutes, right? And units is a field, so it's everything other than 0, right? Mod, sorry, there should be Z mod 7Z without 0, right? So note, in general, right? This generalizes to, there was nothing special about 7, right? Other than the fact it was prime. So Z mod PZ is a field. Yeah. So let me just ask a quick question. What about Z mod like P to the 5th Z? Is this a field? What about like powers of a prime? Oh, sorry, P prime. P prime. So when P is prime, is Z mod P to the 5th Z a field? No, right? I mean, not everything is co-prime with P to the 5th, right? Because P to the 5th is no longer prime, right? So, for example, like P to the 4th, GCD of P to the 4th and P to the 5th is P to the 4th, right? So you certainly have non-units here. Everyone good so far? Okay, so I want to go over as many examples as possible so we're all clear on definitions. So let's do something harder. Let's take the set S to be, I'm taking this from the book, by the way, but A plus B root 2 such that AB is in Z, right? So this is my set. So let's take S under addition and multiplication. Is this a ring? So I'm certainly close, right? Because you know, yeah, it's a ring, right? Because certainly I'm still close because if I add two things, I could group it like this, right? Root 2. I mean, both are in Z, so this whole thing is in Z. Both are in Z, so this whole thing is in Z. So it still belongs to the set, right? And similarly, if you multiply, right? What is this? I'm bad at multiplication. AD root 2 plus BC root 2 plus 2BD, right? I can group it like this, right? This is the first part, plus AD plus BC root 2, right? Now, all of these are in Z, so this thing's in Z. All of these are in Z, so this thing's in Z. So it still belongs to my set, right? So plus and times is certainly a binary operation. Yeah. And obviously, you can check, it's, A plus B root D root 2 plus C plus D root 2. It commutes, right? So it's certainly an abelian group under addition, right? So this is a ring. So what about division ring? Let me erase this. So I just wrote this to convince you all it's a ring. So so what are the units here? What do I need to multiply to get 1? So what do you learn when you see square roots in like math 2a, 2b? How do you make it an integer? Or for example, if I gave you 1 plus I, what do you multiply by to get like an actual like integer? The conjugate, right? Like 1 minus I, right? So this is 1 squared plus 1 squared, right? It's 2, sort of, yeah? So here we're going to sort of multiply by the conjugate, right? A plus B root 2 times A minus B root 2. So what is this? This is A squared minus B squared. So it's A squared minus or root 2B squared. So root 2 squared is 2B squared, right? Everyone agree? So you see, to get 1, I need to multiply by this, right? So this is now 1. Let's put the equal sign. That looks ugly. Let's put the equal sign. Does everyone agree? This is sort of like the inverse, right? Now here's the issue, right? This element is need not, might not. Let me just, instead of say not, let me just say might not be an S, right? Because this element I underline, you could group it like this, right? Sorry, that looks ugly. A squared minus 2b squared. You all agree? And these need not, let me say, might not be in Z, right? Everyone see that? Yes? No? So you see, there are elements, certainly you cook it up, right? Such that the inverse does not exist inside my set, right? So this is not a division ring. And so it's not a field, right? And obviously the units are like, let me just say those where, you know, the circled things are in circled terms are in Z, right? So yeah, I don't know how else to categorize that. So Okay, let's do one more. So set S is R times I, where R is an R. So these are the set of pure imaginary complex numbers, yeah? So question, is this a ring? Yes, no. Yeah, good. The answer is no. Why?
I squared.
Yeah, like basically if I take R1I times R2I, I get negative R1, R2, right? And this is not an S, right? I'm not closed under multiplication. So it can't be a ring. And obviously, if it's not a ring, the other questions don't apply, right? It's obviously no, because units, division ring, fields, they're all part of, you need to have a ring to even ask that, right? So this is no. Okay. Is everyone clear on or is everyone clear on these definitions, right? Division ring, field, units, they'll come up again in the future. So okay. Yeah. Okay, so now let's continue. So how do we characterize, Z under plus under times, right? Because it's different from Q under plus under times, right? As we saw here, right? Like if you compare these two, Q is a field, but Z is not, right? But Z still has very nice properties, right? Even though not everything's invertible, even though it's not a division ring, right? It doesn't have zero divisors, right? So how do we characterize like non-division rings that are like not zero divisors, right? That have no zero divisors. So, whoa, sorry. So we call this an integral domain. Domain D is a commutative ring with unity. One not equal to zero. So whenever the book writes this, it's just saying it's just not the trivial ring, right? The zero ring. So the ring where as a set it's just the element zero. And contain no zero divisors. Yeah, so the integers are an example of this, right? Integers, multiplication commutes, it's a ring with one, right? And it doesn't have zero divisors, right? Because if a times b is b times, if a times b is zero, one of them has to be zero, right? So, okay. Let's continue. All right, so let me remind you that, reminder, right? In non-integral domains, right? In stuff with zero divisors, domains, zero divisors cause issues, right? So I think your professor went over yesterday. There's no cancellation in it, and it's like the analogy of this, right? So, this is a book example because I don't think this example is pretty good. So, you just take this, right? So what you do is you say, okay, let's factor this to this, right? There's two ways to write this, right? When I write, maybe I'll write it both ways, right? So when I say it's equal to 0 in z mod 12z, I'm basically saying this, right? Congruent to 0 mod 12. So it's just another way to write it, right? So here, right, if this was the integers, you would say x equals 3, x equals 2. Does everyone agree with that? Yes, no, if it was over z, over the integers. And that's because what are you using? You're using the fact it's an integral domain, right? So if a times b is 0, one of them has to be 0. So either x equals 3 equals 0, in which case it gives you this, or x equals 2 equals 0, in which case it gives you this, right? But in non-integral domains, it's possible for a times b equals 0, but a not equal to 0, b not equal to 0. So it's possible two non-zero terms give 0. For example, here, x equals 6, right? 6 minus 3 times 6 minus 2, that is actually 12, which is 0 in z mod 12z, right? So there could be like more solutions than you think. Okay, so that's just a reminder, right, to everyone, why we don't like zero divisors. So let me just say in general, let's just say informally fields are the best, are best to work with. Okay, so I'm gonna go over one last thing and then we'll do some examples and then we'll call it a day. So characteristic of a ring. So this will come up time and time again, yeah? So it's important to know, right? So let R be a ring. If there is a positive integer n such that n times a is 0 for all a in R. So it's not enough for like one particular element, it has a hold for every element. Then the least such positive integer is the characteristic of ring. So this will come up again when we go deeper in the fields, but and then we say if no such n exists, R is characteristic 0. Yeah, so I'll go over what this means in like 2 minutes. But you see here, when you first read this, right, you say, oh, I have to check for like every element in R. Like, what if R is like infinite, right? How exactly are you going to check this? So let me just say there's an easier criterion, right? If R is a ring with 1, ring with unity, it's basically saying you just need to check it for 1. So if n times 1 is 0, for some n in positive integer, right? Then smallest one is characteristic. So this theorem is saying you just need to check it for 1, right? Instead of for all a, right? And then if n times 1 is not 0 for all n, then R is characteristic 0. So let's do example. Find characteristic. Okay, so let's do something easy, right? Let's find characteristic of Z. So let's use this criterion here. Is there any integer I multiply to 1 to get 0 in the integers? Positive. So by positive, we mean strictly bigger than 0. So is there any number bigger than 0 that when I multiply it to 1, I get 0? So this is characteristic 0, right? Because no such n exists, right? So what about z mod nz? Yes, z mod nz. Is there any number I multiply to 1 such that I get 0 here? N, right? N times 1 is 0. In fact, n, 2n, anything with factor n does it, right? But we want the least one, everyone, right? The smallest one. So which one is the smallest one? You could check its n, right? Because anything smaller times 1 is non-zero, right? So this is characteristic n. Yeah. So so let me just say things to examples to have in head. Is characteristic 0 includes stuff like integers, rational numbers, complex numbers, real numbers, right? And then characteristic n is like z mod nz, right? So let me ask 2 more questions on this. So let's do something harder. So you all learn products, right? So what is the characteristic of this? The product of this. Plus times. So obviously plus means the plus in each one, right? Plus component wise, right? So is there anything I can what is 0 here? 0 here is 0, 0, right? So is there any positive integer n I can multiply to like AB to get like 0, 0? Is that possible? No, right? It's certainly possible on the second component, right? Like multiples of 5. Agree? But no such a thing. You'll get like NA 0 at some point, but you'll never get 0 on this component, right? I'll agree. So this is characteristic 0. Now, what about something like 7z? What is the characteristic here? I think I tricked you. So this is characteristic 0, yeah? Who was it? So Jacqueline, I think you're Jacqueline, I think you're thinking of this, right? 7. This is 7. I think that's what you're thinking of, right? So this is characteristics 7, right? But this and this are like 2 different sets, right? This is like modular 7. This is like all multiples of 7, right? So this is like a subset of the integers, right? So, and you could check that no matter what you multiply, you're not going to get 0 here. Because I mean, you don't get anything for all the integers, so you're obviously not going to get it for a subset of the integers. Okay, let's do one more. So this is something cool. You'll encounter it when you learn more about fields later on. So let R be commutative ring with unity of characteristic 3. Everyone is okay with me doing this, right? From now on, like just shorthand CHAR for characteristic. Okay. Simplify A plus B times 9. No, not times 9. 2 to the 9th power. So how about this? Do you all know the? Oh, maybe there's a bad question. Do you all know the binomial formula? Do you all know that, like, for example, a plus b cubed is 3 choose 0 a cubed? This might require you to know this, but yeah, you all know this, right? So let me do this thing first, right? So this thing right here, right? 3 choose 1, right? That's 3 factorial over 3 minus 1, which is 2 factorial, 1 factorial, right? So do you all see that these two terms here, and obviously 3 choose 0, anything choose 0 is always 1. Anything choose itself is always 1. But do you see here, like, these terms, they're all divisible by 3. Do you agree? Because binomial coefficients are, like, always integers, right? And you see here, there's nothing that can cancel out with the 3 right here, right? So again, this is, if you like, 3 times 2 times 1 over 2 times 1 times 1. 1 factorial is just 1, right? So let me just say, like, 9 choose 7, for example, right? That's like 9 factorial, 2 factorial, 7 factorial, right? So let me just write this. Let me just convince you all. 6 times 5 times 4 times 3 times 2 times 1. So 7 factorial is just this thing, right? Yeah. So do you all see that, like, other than, like, 3 choose 0 or like 3 choose 3, like, everything's divisible by your top number? Does everyone see that? Yeah, that's what I'm trying to get at. So a plus b to the 9 is just this, right? So so if you see this problem, please do not, use a calculator and multiply everything out, right? There's so a to the 8, b, let me just write the first few. 9 choose 2, a to the 7, b squared, plus plus. Let me just say 9 choose, let's do 9 choose 7, a to the squared, b to the 7, 9 choose 8, a, b to the 8, plus 9 choose 9. Okay, hopefully you all know 9 choose 9 is 1, right? So this is just b to the 9. And a to the 9 is just 1, right? So do you agree that all of these are divisible by 9? Do you all see that, at least from, like, me showing you 9 choose 7? Because, like, there's nothing that will cancel out with the 9. Like, even like 9 factorial over, like, 8, 9 choose 8, the 8 factorial will cancel out with, like, the 8 here, but nothing's going to cancel out with the 9. So, but if all of these, everything in red divisible by 9. Red underline. What is that now? Because they tell me I'm in characteristic 3. So I know 3 times everything is 0. So 3 times A equals 0 for all A and R, right? That's what it means to be characteristic 3, right? So if 3 times A is 0 for all A and R, well, 9 is just 3 times 3, right? So this is just 0. Yeah. So you see that this thing is just a to the 9, the term right here, and b to the 9. That's it. Because the rest are divisible by 9. You're in characteristic 3. So you're all the terms with 9 in it go away, right? So this is like so this is your answer. It's just a to the 9 plus b to the 9. Everyone clear with that? So binomial theorem really simplifies in characteristic not 0, right? In integers and like complex numbers, real numbers, you have to FOIL it out, right? Because nothing cancels. You're in characteristic 0, right? These are characteristic 0 rings. But when you're in, say, like characteristic like 3 is just 0 basically. So if 3 is 0, like here, like z mod 3z, right? Z mod 3z is characteristic 3. If 3 is 0, then obviously 9 is 0. And basically everything in the middle goes away. Yeah, it does, I think. They define anything that, yeah. If no such n exists, they say it's characteristic 0. At least that's what it says on my book. Yeah, they're not going to say characteristic infinity. So, okay, is everyone clear? Hopefully that gives you more intuition on structures of rings, how we categorize rings differently based on like characteristic, integral domains, fields, division rings. Yeah. So next time I think we're gonna go over like applications of like Fermat little theorem and stuff like that. Okay. That'll do it for today. I'll see you all Thursday.